on this page for single displacement, put a little star at the top of the page. This is one of your more important types. How many of you have had lab this week already? Anybody? A few? A couple? All right. Our first example here, I was hoping more of you would have by the time we did this, but that'll be okay. This first example is one you did in that experiment. And if you've not had lab this week, then kind of keep this reaction in mind when you get toward the end of this week's lab, because you'll see this reaction going on. But what you've got with single displacement is that you have an element plus a compound, and the products are you get a different element and a different compound. Because there's an exchange that takes place. So, in the drawing, before putting it in reaction form, this is our solution. This is our copper 2 sulfate floating around in the solution. And we've got zinc metal. So, zinc as a solid plus copper sulfate solution. And we're looking at what the reaction is going to be as far as displacement goes. Displacement means replacing, taking the place of. What happens in this process is you've got copper that's positively charged and in solution. And you've got neutral zinc, which would like to be positively charged and in solution. Zinc is a metal, correct? Metals like to be cations. And so the competition here is between copper, which is already charged and in solution, and zinc that wants to be charged and in solution. And so the process is the zinc goes in and the copper comes in. The zinc forces the copper out of solution. So what you wind up with, I guess picture-wise, is copper solid and zinc ions in solution. So that the zinc goes from being solid to dissolved, the copper goes from being dissolved to solid, and what does the sulfate do? Nothing. Nothing. The process here would be written like this. And this is a little simpler than most because zinc and copper just both happen to be +2 charges. And so we don't have to worry about balancing. That one kind of falls in place. But just as a first example, that's the way single displacement works. It's a competition amongst positives over who gets to be the one in solution. Now in the notes, you've got this activity series. I'm sorry, question? In the notes, you've got this table that's labeled as the activity series. And that's your ranking over who's more powerful. So toward the top, meaning more powerful, more able to get in solution, and further down the chart is worse. So who's number one? Lithium. That means lithium is the strongest. Nobody pushes lithium out of solution. And it is strong enough it's going to beat all the others. All right? So lithium's number one. If you're a sports fan, you can make lots of good parallels to this. Out beside lithium, write down Alabama football. Because that's the way it typically works out. They still have a chance this year. Down below, see where gold is? Mark out about 5 more notches below gold and write in Tennessee football. And that's going to be usually appropriate.
South Carolina's flooding this year.
Sorry.
South Carolina's flooding this year.
Well, we'll blame that on the flood. And the power outage and all that stuff. If they're lucky, they may work their way, Tennessee may work their way up above 10, but I doubt it. I doubt it. Think of this as the power rankings, all right? The top one, the higher ranked one, always wins. So, find zinc and find copper on this list. Copper is the fifth one up from the bottom. Where is zinc? It's about a third of the way down. Yeah, okay, thank you. So who's higher ranked? Who's the more reactive element? Zinc. So if zinc is in competition with copper, who's going to win? Zinc. Which means zinc will be the one at the end of the process that is charged and in solution. And so that's how you can predict that this change is going to happen. If you've got copper in solution and zinc is a solid, that exchange is going to happen. If you started out with copper solid and zinc in solution, is anything going to happen? No, because the stronger one gets to be charged and in solution, and the stronger one is already charged and in solution, correct? So there won't be a reaction for this one. No reaction. So you use this chart to make your predictions. Right? Oh, no, I would not do that to you. No, that would be mean. You'll have this exact chart printed on the exam, okay? But you need to do enough of these to where you're comfortable and quick at using it so that you know what's going on. Now notice that everything on this list is a metal with one exception. And who is our customary exception?
Hydrogen.
Hydrogen. 1, 2, 3, 4, 5. Sixth one up from the bottom is hydrogen. Even though hydrogen is a non-metal, it does typically form positive charges. And so this is a list of positives, not necessarily a list of metals. All right? This is competition amongst positives, most of which are metals. But hydrogen is in that list as well. Problem number 8. At the bottom of the page is asking you to do a couple of these single displacement ones. So for now, do this one. You should always balance them. On that first one, we didn't have to because it just worked out. It was automatically. But you should always balance. It's a gas and it's diatomic.
Do you put a G by it? Is it okay.
Well, it's on the product side, it will be H2
Okay.
because it's coming out neutral. It doesn't start that way because it's part of a compound, but it does wind up as H2.
I mean, like we're putting an S by zinc because it's solid, but when H comes out, do we put
Oh,
a G by
G
it?
for gas.
Okay.
Zinc with hydrochloric acid, will there even be a reaction? Yes, because zinc is higher ranked. So it's going to force its way into the compound. Hydrogen comes out as the plain neutral element, diatomic hydrogen. And your product you build based on zinc being exclusively +2, chloride being exclusively -1, which means this for your formula, not ZnCl. Just because this was 1 chlorine in the compound doesn't mean your product will be. You piece that together based on charge. Now, we haven't balanced it yet. We'll do that in a moment, but that's getting your proper formulas on the product side. Yes, there's going to be a reaction. Write down the formula for the element. Happens to be diatomic. Use charges to figure out the product, the other product, the compound. Question getting to that point. How would you balance it? 2 here, and that would take care of it, right? Okay. Question about this one? Right. Yes.
Can you talk about how you broke it down in the product part?
What we're looking at is zinc and hydrogen switching places. So hydrogen has to come out as the element, and it is one of your 7 diatomic elements. But that means that zinc gets a hold of the chloride. And the charges being what they are, it can't just be ZnCl, because that wouldn't be neutral. Each zinc is going to have 2 chlorides with it. And you know that based on the charges of those 2 particles. And so once you've got that ZnCl2 formula built, that's when you start thinking about balancing. And that's how you know that you need 2 chlorines, so you put a 2 here. That also gives you 2 hydrogens, which is what you needed anyway, and winds up being balanced. And the next one, zinc with aluminum chloride. Will there be a reaction? No, there won't. Okay. No reaction.
How do you know why it's more
If you're comparing zinc and aluminum, aluminum's higher ranked. Aluminum is 2 spots above zinc.
So aluminum is higher?
Aluminum is higher. And there it means it gets to be the one in the compound. And it's already the one in the compound. Question about that? There won't always be a reaction with single displacement. You use this activity series to tell you if there's going to be a reaction or not. And actually, the chart even helps you with charges, because it tells you over there Li plus or Ca2 plus and Fe2 plus and so forth. So it helps you with charges there as well, in case you forget one or freeze up on charges. Question about single displacement, about how it works. Now, before we move on, I'm going to put one more thing here on the board. And this is just, don't anybody write this down, okay? Because this is not going to be something I would test you over. But I just want you to think about it a little bit. In relation to that activity series, This is also single displacement. But who is that bromine in competition with? Not the aluminum, chlorine. Because these are both nonmetals and they want to be negative, right? That activity series helps you with single displacement of cations. In this case, we're dealing with a nonmetal. Nonmetals want to be an anion, so the bromine's in competition with the chlorine. This would be competition amongst negatives. Now you've got an activity series that ranks your positives that way, but they don't have an activity series of negatives. And that's because the pattern looks something like this, where fluorine is the most reactive, followed by chlorine, followed by bromine, followed by iodine. There's your activity series.
Does that have anything to do with electronegativity?
It has everything to do with electronegativity, yes. That's right. The more electronegative ones are the ones that are dominant, the ones that are in control, and they can force their way into the compound, meaning they can force the other guys out. Is bromine strong enough to force the chlorine out? That would be no reaction, correct? Well, no, let's keep that bromine. But if this had been iodine, aluminum iodide, would there be a reaction?
Yeah.
Yes, there would. Okay. Do you see how that's similar to what we just did with cations? I promise, I will not test you on single displacement of anions simply because we don't have the time to put into it and do a lot of repetition with these. But I just want you to know it's out there and it works very much parallel. Question about single displacement at all? All right. Double displacement. With double displacement, you're dealing with two compounds. And you're getting two different compounds. So what's going on physically, if this is your beaker, we're putting in silver and nitrate. We're putting in copper, 1, and chloride. And so when you take these two small solutions and dump them together to make one big solution, you've got the potential for reaction. And generally, these reactions, double displacement, is pretty much solubility-based processes. Because what happens when you put these two solutions together, it just happens that silver ions and chloride ions are not compatible with each other in solution. And so those will precipitate out as a solid. The copper 1 and the nitrate, those are fine together. But the silver and the chloride cannot coexist in the same solution. They'll attach, they'll bond, they'll precipitate out. And so you start with everybody in solution, but you end up with a solid that you didn't have before. So double displacement, most of the time, is a solubility-driven process where you form a solid. Not exclusively, but usually. That's going to be what happens. So you need to be able to look at your possible compounds and know, are they going to be solids or are they going to be aqueous, meaning still soluble? And what you compare then is silver possibly bonding with chloride, copper possibly bonding with nitrate. You consider those as your possibilities. And in the notes, you've got table 4.2, table 4.3 for you to look at and make these kinds of comparisons to see who's soluble in water and who's not. Rule number 1. Compounds containing an alkali metal cation like lithium, sodium, potassium, rubidium, cesium, or the ammonium ion, those are going to be water soluble. All lithium, sodium, potassium compounds are water soluble. Notice over to the right where it says insoluble exceptions. There's not any exceptions to that first rule. But unfortunately, that first rule is not relevant to this particular reaction because we don't have any alkali metals, correct? Second rule talks about the nitrate ion. Now that's relevant to this because when we're considering the possibility of copper 1 bonding nitrate, look at that second rule. Compounds containing the nitrate ion are water soluble, correct? Is copper 1 an exception to that? No, there are no exceptions to that. And so that's a water soluble substance. That's why we still have it up there as copper 1 nitrate aqueous. It's not going to form a solid. The next rule down, if you keep reading down through these rules, you're going to see you don't have a silver rule. But you do have a chloride rule. Rule number 3 talks about the chloride ion. Compounds containing the chloride ion are water soluble. There are a few exceptions, and silver is one of them. Most chloride compounds are water soluble, but silver chloride is not. And so that is what tips you off that this silver chloride is going to form a solid. And that's the driving force for the reaction. The silver and the chloride will bond together and form a solid. That's what makes it a true reaction. And this one is coincidentally already balanced. Go ahead.
Will it always form a liquid and a solid?
See, sometimes you might form 2 solids, maybe. Sometimes when you go through these, when you compare to those rules, it may end up telling you that they're both aqueous. And if that's the case, then it's no reaction. Because if you put the 2 together and nobody's incompatible, then they all just stay floating around in the beaker together and you don't really form a product. So if they both predict out as aqueous, then that would be no reaction.
Will we give them this table as well?
Yes. Exactly like it is here in the notes. Number 9. Balanced chemical equation for a reaction of ammonium chloride and potassium sulfate. ammonium to sulfate, potassium to chloride. Hopefully you're not writing down any products. Because ammonium with sulfate, rule number 1 tells you that that would be a soluble compound. And potassium with chloride, rule number 1 also tells you that's a soluble compound, right? So this is one of those that's no reaction. You take the two little solutions, you jumble them together, make one big solution, and that's all you get is one big solution. You end up with a mixture, but not a reaction, because nobody's bonding anybody. There's not going to be any product formed here. This is going to be a no reaction. Question about that? Yes?
Can you explain no reaction?
There's no, when you make the comparisons here on your predictions on what could form, and you compare those compounds to the solubility rules, they both predict out to be water soluble. And if everybody starts as water soluble and ends as water soluble, then they haven't really changed. You're looking for a change in physical form. Somebody that would form a solid, and neither one of these will.
So essentially you're looking for the exceptions, right?
Yeah, you're looking for a solid to form. Do the second one. Will there be a reaction? Yeah, there will be this time. And for no particular reason, let's just start with barium and work our way across the reactants there. When you look at barium and you scan down your list of solubility rules, you don't have a barium rule. But what you do have is a sulfate rule that tells you compounds containing the sulfate ion are generally water soluble, but there's a few exceptions. And barium is one of those exceptions. Barium is not soluble in the presence of sulfate. And so that's going to form a product. You piece together its formula based on charges. These are coincidentally both magnitude 2. BaSO4 solid. That's the driving force. That's what causes the reaction. Question. The other substance then is going to be potassium with chlorate, which is coincidentally balanced already to magnitude of 1. Is that going to be water soluble? Rule number 1 tells you that all potassium compounds are soluble. And if you accidentally overlook rule number 1, then rule number 2 tells you the same thing, right? Rule number 2 says that chlorate compounds are all water soluble. So either one of those rules is going to tell you those particles remain aqueous. That's predicting your compounds, piecing them together to make the neutral based on charge. That's everything but the balancing. We haven't done the balancing yet. But is our question getting those products predicted? Those solubility rules will tell you if there's a reaction or not. And if there is, then you build your products based on charge. Just like we did previously. All right, balancing, 1 barium, that looks good. 2 chlorates, 1 chlorate. Put a 2 here.